In this video, we will study session 9.4, test for convergence. So in the last session, we compared a series with an integral to determine whether or not the series converges. Now we compare two series. We have the following comparison test. Suppose an greater than or equal to 0, less than or equal to bn for all n beyond a certain value. Then we have the following conclusions. If the sigma bn converges, then sigma an converges. If sigma an diverges, then sigma bn diverges. This is called the comparison test. So now we use the comparison test to do an example. So decide whether the series converges. So I want to find another series to compare with this series. So we know n cubed less than or equal to n cubed plus 1 for n greater than or equal to 1. And 1 over n cubed plus 1 is less than or equal to 1 over cube for n greater than or equal to 1. This greater than or equal to 0. We know sigma 1 over n cubed and from 1 to infinity. This is a p series with p is 3 greater than 1 and so convergent. Then we have this series convergence, so this series is also convergent. That's the sigma 1 over n cubed plus 1 and from 1 to infinity is also convergent by the comparison test. So this is the comparison test. Next we introduce another test. It's called the limit comparison test. It also can be used to confirm a prediction of convergence or divergence. So it's called the limit comparison test. So suppose an is positive and bn is also positive for all n. If we have limit an over bn, n goes to infinity is c. C is positive. Then the two series sigma an and sigma bn either both converge or both diverge. This is called the limit comparison test. So now we use the limit comparison test to do an example. Determine if this series converge or diverge. N squared minus 5 divided by n cubed plus n plus 2. So for this series, we have an is n squared minus 5 over n cubed plus n plus 2. So if n is very large, so n behaves like n squared over n cubed. If n is very large, that means the numerator is denominated by n squared, denominator is denominated by n cubed. So an behaves like n squared over n cubed if n is very large. So we take Bn is 1 over n. So now we use the comparison test. So we look at the limit an over bn as n goes to infinity. So an, it's n squared minus 5 divided by n cubed plus n plus 2, then divided by 1 over n goes to infinity. And this is the limit n goes to infinity. N cubed minus 5n divided by n cubed plus n plus 2. So this limit is 1. Limit is 1, so that means c is 1. The limit comparison test applies with c is 1. So this sigma an and sigma bn have the same convergence or divergence. So since sigma 1 over n, this series diverges. This p series with p is 1. The limit comparison test shows that sigma an, that is n squared minus 5 divided by n cubed plus n plus 2, also diverges. So next we look at another theorem. This theorem tells us if the absolute value of this series converges, then so does sigma an. So now we look at an example how to use this theorem. So if we have this kind of series, so this series is 1 minus 1 false plus 1 over 9. So this series has both positive and negative terms. And we have an is negative 1 and minus 1 over n squared. So the absolute value an is absolute value negative 1 and minus 1 over n squared. So this is 1 over n squared. So we know the p series sigma 1 over n squared. This p series converges. So by this theorem, we have sigma negative 1 and minus 1 over n squared convergence. This is how to use this theorem to determine whether or not the series converges or not converges. So next we introduce the ratio test. Next one is called the ratio test. So for a series, suppose the sequential ratio has a limit, that is limit an over absolute value divided by an absolute value. N goes to infinite. This limit is L. If L less than 1, then sigma an converges. If L greater than 1, or if L is infinite, then this series diverges. If L is 1, the test does not tell us anything about the convergence. Of the series. So now we use the ratio test to show a series convergence. Look at this example. Show that the following series converges. Sigma n from 1 to infinity over n factorial is 1 plus 1 over 2 factorial plus 1 over 3 factorial. So we have an is 1 over n factorial. Now an plus 1 is 1 over n plus 1 factorial. Then the absolute value n plus 1's term over the absolute value n's term. So look at that this ratio. This is 1 over n plus 1 factorial divided by 1 over n factorial. Simplify, get n factorial divided by n plus 1 factorial. So the n factorial is the multiplication of first n natural numbers. So it's n times n minus 1 times n minus 2, 2 times 1, n plus 1, n minus 1, 2 times 1. So we cancel n minus 1, n minus 2, 2, 1. So we get this is 1 over n plus 1. So let n goes to infinity. So this ratio will goes to 0. 0 is less than 1. So 0 less than 1, 0 is this L less than 1. So then we have the series converges. Because the limit is 0, which is less than 1, so by the ratio test, the series 1 over n factorial and from 1 to infinity converges. So next we look at the alternating series. A series is called an alternating series if the terms alternate inside. For example, the series n from 1 to infinity, negative 1 to n minus 1 over n. So the series is 1 minus 1 half plus 1 third minus 1 fourth, negative 1 n minus 1 over n. So the convergence of an alternating series can often be determined by using the following test. It's called the alternating series test. So this test says that an alternating series of the form this is A1 minus A2 plus A3 minus A4 convergence if its terms decrease for all n and its limit as n goes to infinity is 0. This is called the alternating series test. You have the terms decreasing, terms is positive and terms is decreasing, and its limit is 0, then the alternating series converges. So now we look at an example. Show the alternating series convergence. So this is an alternating series. We have an alternating series is of this form. So an is 1 over n. An plus 1 is 1 over n plus 1. So we have an plus 1 is 1 over n plus 1. So this is less than 1 over n. This is an for all n. And the limit of an as n goes to infinity is limit 1 over n goes to infinity. This is 0. So by the alternating test, these two conditions are satisfied. So by the alternating series test, the alternating series converges. So we have the alternating series, harmonic series converges.